Welcome back for the afternoon session. Our speaker today is going to be Bin Si from Shinshu University, and he's going to talk about an SPDE with the law of a Levy process as invariant measure.
Okay, thank you very much. Thank you for your kind introduction. So today is I'm very glad to give a talk about the SPDE with the distribution of a Levy process as its invariant measure. This is a joint work with my former supervisor, Professor Tadahisa Funaki. Okay, I also want to take this chance to express my kind acknowledgement to the organizers of this program. They gave me a very excellent chance to attend this program. And during this period, I make friends with a lot of excellent mathematicians and enjoy the life in Cambridge. A very good chance. Thank you very much. So now in this talk, I want to divide it in 4 parts. First, we want to explain what's the meaning of our title. In other words, we want to show what's the purpose of our talk. Then we begin to construct a noise such our goal can be satisfied. Then we can consider a heat equation such as this one. And in the end, we will characterize the invariant measures for our system. Okay. I know that today everyone is expert in this stochastic partial differential equation, but I still want to start with a simple east-one stochastic heat equation driven by a Gaussian space-time white noise. Gaussian space-time white noise. For these equations, we know a lot of results. For example, we can show that if the UTX, the solution UTX, is held continuous in its time with 1/4 alpha Hurd order and 1/2 in time in space. In space. It is well known. This is the one well known. Characterize the solution, or we can say that the regularity of the solution. And another one, it's natural to ask whether it has the invariant measure. Of course, in the morning section, Professor Thomas gave a very excellent talk about the ergodic. Of course, Martin Harry also do a lot of excellent work in this field. But I only want to review for this very simple equation. You know that according to the boundary condition, if the boundary is Dirichlet boundary, you know that the law of Brownian bridge will be invariant measure. If we consider the mix in boundary condition, for example, we fixed 0 equal to 0, and at 1, b equal to 1, it will be free. Then the law of Brownian motion, or okay, say the Wiener measure, is invariant for our system. Of course, this is also reversible because there is no potential. It's a very simple case. Okay, and if we consider the Newman boundary condition, we can know the law of Brownian motion with the big initial measure, initial value measure, the big measure, then the law is still invariant. Okay.
The next case we have Neumann on the right.
Yes, you are right. The mixing. The end at the point 1, it will be free. The mixing. Yeah. So, right. Sorry. I means for the mixing here, it means that delta ut delta x t1 equal to 0. Okay. This is well known. Just a very simple result from the paper of Naki in 1803. Okay. From this, the stochastic heat equations, there's a lot of generalization. For example, from the linear equation to nonlinear equation, the classical one is the Ginzburg-Landau and Berg's equation or Navier-Stokes equations. And then we considered the generalized it. Generalize this equation from the linear to nonlinear. Or another way is to consider the generator. We can consider the higher order generator or fractional operator. This is another way to generalize this problem. Another one is generalize the noise. You know, there's a lot of mathematicians to pay attention to the SPDE with Levy noise. So here I want to point out some result Brezhnev, and this one I can't pronounce it, so it's too long. And Kamura and Pezet, Rockner, and Brezhnev, of course, including the work of Junji and Dalang for the. So there's also another rough path theorem from the fractional Brownian motion. Okay. Of course, there's another lot of generalization. In our case, I want to generalize in the viewpoint of invariant measure. So if we consider the mixed case, mixing the boundary condition, we know the law of Wiener measure. Wiener measure is its invariant measure. So it's well known the support of Wiener measure in our case, in our special case, it's just continuous function space. Of course, you can see it will be alpha Hurd continuous 1/2. So our question will be this one, the following: whether can construct a stochastic heat equation or stochastic partial equation its invariant measure with the support in this space, the Cadillac function space. So this is our goal. This is our purpose. Okay. I will, of course, I have said that a lot of work, sorry. I have said a lot of work about the stochastic heat partial differential equation driven by Levy noise, just as like this one, the OU process. Here LT denotes a Levy process in some Hilbert space. Of course, for this case, they know under some conditions on the generator A, you can know that its invariant measure will be operator self-decomposable. But we can't, from the result, know anything about the support of the invariant measure. In fact, we can show that if we considered a heat equation instead of the Gaussian space-time white noise by a Levy noise, we can show the path UTX. For each fixed t, the x will be continuous. This is, in fact, when I considered our question, we can't know such result, but we foresee it will be true. When I come here, I was told by the Professor Brzezinnik. In his paper, he showed that the space, it will be continuous in space. I will explain it later implicitly. Okay. Now, instead of the bounded interval, I want to consider a stochastic heat equation on the half line. So, as I explained, our main question is just this one. Does there exist a noise such such that the law of a Levy process is invariant under the dynamic system? Okay, here the law denotes mu A B nu. It just denotes one-dimensional, the law of one-dimensional Levy process. Okay, here the nu is the Levy, in general, the Levy measure. And the A we required is a positive. I mean, positive is large or equal to then 0. Equal to 0. Okay. This is the fact, the motivation, the first motivation I have explained in there. If we consider the bounded interval and the Gaussian noise, the law of Brownian motion will be invariant. Okay. Another one is based on this. This it is just obtained by the Professor Ito. He tells us if we consider a Markov process starting from a Poisson random measure, then we can consider the counting process. This denotes the time t. So he tells us if the diffusion is a Markov process, then at any time the counting process is still a Poisson random measure. For our case, we consider the Poisson Markov process is nothing but the reflecting Brownian motion. Okay. Based on this result, formally, we can define the function UTX because Pt bar is a Poisson random measure, so this function, in some sense, it's well defined. So we use the E2 formula. We can show that the law of a Poisson process is invariant for the heat equation with this noise. Of course, here the delta means the delta distribution is in the generalized sense. We will explain it formally. In fact, UTX by the definition is nothing but this one. So we consider the inner product for the test function phi with 0 equal to 0. Then we can use the E2 formula, simply get this one. Okay, so we can explain our equation. Now we take the place, this one, in the weak solution. Weak sense. It is a stochastic heat equation, and its invariant measure is nothing but the law of Poisson random measure.
The formula for NT again, the initial, the random measure there.
Yeah, of course.
Can you
Yeah, of course.
Can I see?
Pardon, please.
So you have a Poisson process and you started random motion from the point of the Poisson process. Is that right?
Yeah. Of course, we start the Poisson random measure. Okay. Based on these two motivations, from now we construct our noise. How to do? Just as our simple observation, we considered also a Poisson random measure on this product space. Here W0, we denote a continuous function with 0 equal to 0. It's just it's nothing but the Wiener space in the function space. And the intensity measure equal to this one. This is the Levy measure, and this is the Lebesgue measure. This is the Wiener measure on this product space. Okay. So you know that it is not just a Poisson random measure, so it has a countable support. Formally, it can be write as this one. Now we consider the noise. This is our noise. Here, M, formally we defined it by this one. Compare our simple case, here equal to 1. It's nothing but the jump size of the Poisson process. Okay, now instead of 1, we consider the random jump size. It's our main goal to explain this term, to make it has the meaning in our case. Okay, W is the cylindrical Brownian motion as usual. Okay, here BIT denotes the reflecting Brownian motion. Satisfied, of course, it is nothing but the solution of Square-Hall equation. Here the initial value, it will be start from yi. This is, for each I, it will be start from this initial value. Okay. So there is another approach to construct the noise. Okay. In this case, until now, we construct the noise mass. Firstly, we reflect the Brownian motion. Another way, we consider the noise, the path, just start from the initial value yi, but the path will be positive or negative. Then we reflect it the noise. Okay. Yeah, I have remarked that there's a lot of work with a Levy type noise. I want to explain that. We will see that our noise is very different from the Levy type noise. It's very different, okay? And in fact, for our noise, we will consider the integral for all the time, for all the information before time t. So our noise will have some memory. It's not independent increments. The SPDE driven by the Levy noise and characterize its invariant measure recently considered by Chonuska, and the Rockner is co-authors. Okay. Now we consider the property of our noise. Because our noise is defined, formally defined by this one. This is a series, so we must give some meanings such the sequence will be convergence. Okay. Into shows it, we decomposed n into two parts. The first one, we based on the size of jump. Okay.
Can you show again the 1, 4?
1, 4. This one is just I write down. Oh, sorry, minus. And for the convergence is the same also, but the minus.
When you say that M1 is for psi I larger than 1,
Yeah.
And the other one is for smaller,
Yeah.
you mean that M1 is for all psi 1 bigger?
You mean this one?
Yeah, so
You know that our Poisson random measure with the intensity is nothing but the Levy measure, the big measure, and the Wiener measure. So I want to divide our noise according to the Levy measure. Yeah. So the jump size will less than 1. I will divide it in many times. It's just the usual case, usual idea to prove the Levy to decompose theorem. Okay. And this means the Cauchy-1. This with the law of d Cauchy A1. Mu A1. Where A1 is nothing, the jump size larger than 1, the set. Okay, just the idea is just according to the Levy, one-dimensional Levy case, n-dimensional Levy case.
But the sum, when c is smaller than 1, must be compensated. You must subtract the expectation of the jumps when c is smaller than 1.
Yeah.
In order that you make it summable.
Yeah, of course. Yeah. So in fact, we will, if the jump size less than 1, we will divide it again according to the jump size larger than 1 over n. Right, 1 over. For n larger than 2, divided it. Okay, here. So we must give the meaning for this. What's the meaning it will convergence in what means? So to do that, we assume this one condition. Here, our condition is only give on the decay of Levy measure with very weak conditions. Here, for large key, there is a large key and a small kappa larger than 1. Okay, it means, of course, the Levy measure of according to the alpha stable, it will satisfy this condition. Okay, here is our first proposition to show that the jump, if the jump size is larger than 1, we can show that it's for test function, for any test function, satisfies this condition. Then it will, the sequence will be convergence uniformly in T. Here the Cauchy I1 I have explained it. It's just the law, the random variable of this one. You know that according to the Poisson random measure theory, all of the random variable, random vector, it will be independent. To show this, we just give some estimate for the Poisson random measure. Here we just used the distribution of yi, because the yi is nothing we know. It's just the gamma distribution, the variable. We used the property we can give. For each I, they will be decay just like this one. And this is the trivial one. I will omit it. Okay. To show the almost surely convergence, we used the Broglie-Contley lemmas. So in fact, for our conditions, it's just to show this one will be convergence for this part. Here we use our some portion A here only for this part. Okay, but just if the jump size less than one, it will be easier to control, because it's for the jump size, we know that the Levy measure for the Levy process, it will be integrable for any moment. So we can easily to show that if for M2, I mean M2 is for the all of the jump size less than 1 for the summer. This is nothing but a continuous orthogonal martingale measure. And of course, based on the theory of Wallisch and Professor Dalan, we can consider the stochastic integral, E2 integral. But here for our goals, we only consider the Wiener integral. I mean, for Wiener integral, I mean that the integrate will be deterministic. Here, we know that for each fixed phi Sx, there is a coefficient. It's nothing but the Levy measure, the integral in the jump size less than 1. Okay, this property is very easy to show. Here, I want to say that our quadratic variation process, in some sense, is random, not deterministic. Okay. Based on this, the two propositions, we know that for any test function or good test function, the sequence will be convergence almost surely. So we can consider the stochastic heat equation driven by our noise. So for our goals, we introduced the two kinds of definitions of solution. One as usual. One is the weak solution. For the weak solution, as usually means that for the test function, this integral equation will satisfy. Here, the character is we required the path will be continuous as the L2, the weighted L2 space valued process. Of course, if you consider the Levy type noise, it must have some jump. Anyway, it can be continuous. In this sense, we also see that our noise is not a Levy type noise. Usually, this is a mild solution. Also, it's very easy because it's just, in some sense, Einstein-Uhlenbeck process. Okay. If this satisfies this equation, it will be said a mild solution. In fact, we will show that the mild solution is nothing but the mild solution. So we can show the existence of the noise because our noise is very bad. Of course, for this part, noise is good because we can explain it as the E2 integral. But for the first part, this part, M1 is very bad because there's no integral probabilities because the properties of the jump size. Okay. Now, under our decay, the conditions of the Levy measure, assumption A, then we can show that there is a unique weak solution. In fact, as the noise, we only have to do is show the stochastic, in some sense I called it stochastic convolution process, has the meaning. So to show it, this part is it will be easier because this noise is nothing but the orthogonal-martingale measure. It can be discussed as the Gaussian space-time white noise. But for this part, to show the continuity, we use two times of Kolmogorov regularity theorem. In fact, we only considered for each fixed I. It can be explained very well. And then we show the convergence will be uniformly convergence in time t. For each fixed I, for each fixed, you know that for each fixed I, it's continuous. And then with the uniformly convergence, so the stochastic convolution will also be continuous. This is a different part.
Can you show a little bit more than continuity or just continuity?
Okay. So for this part, we can formally it is nothing but this part minus this is just this sum. So to show the continuity, we only show this one. This part is continuity for t. And then we show this series will be convergence uniformly in t, for t in fixed interval. But for this part, for the continuity, it's very simple because it's just corresponding to the integral with respect to one-dimensional Brownian motion.
Can you show, because that was my question, held the continuity or?
Pardon me?
Is the process held continuous or not?
Held. Yes. It's just, I will give the remark later, okay? Okay. So I think this is your answer. We can show that it's alpha Hurd continuity. It's just like as the Gaussian space-time white noise in time t. It's a one quarter. Okay. Another question is that our noise is not so good. I mean that so as I just explained it has a memory. So the solution can't give a Markov property. Okay, now I want to characterize our invariant measure. Here for I will compare the result with this result. So here I give the weak meaning of the invariant measure. For the invariant measure, I mean, if we consider a U0, the initial value with a distribution mu, mu AB mu. Then for each time t fixed, for each time, it also have the same law. Because this is not a macro process, so we can't define the invariant measure in the usual way. We only considered according to the develop of time, it will be changed their distribution. This is our interest. I also will give the explain if we want to consider the invariant measure support mu in equal in some sense in the Cadillac space. We can't use the Levy noise. Here I give some notations. The first one is the probability measure on our state space. Then I denotes the invariant measure in this sense, in the weak sense. Okay, and the C denote the convex Hall for each given A, the covariance, and Levy measure. Okay. So our first main theorem is that for each Levy measure, the law of Levy process, it will be invariant. The set of invariant measure and convex Hall, the mu A, B, mu for B, the convex Hall. So the first conclusion is that for the convex Hall is a subset of the invariant measure. Our proof is just use some simple idea, just as to do some research for the one-dimensional Levy process. Firstly, we required an additional assumption on the Levy measure. Then we can show that this, because our noise is independent summer, so we can consider the invariant measure independently by part. So under this condition, for any Levy process, we can write it down as this summer.
Excuse me, just can you, I would like to see what do you mean by this statement that the measure mu AB, mu is invariant?
Oh, this for the meaning?
Yeah, what do you mean that it's invariant for SPDE?
Okay, so I just explained it. If the initial value U0 is distributed as the law of Levy process, then for each time t,
okay, thank you. Sorry.
the same distribution. So for this part to prove it, it's just as our introduction for the Poisson random measure, Poisson process case. Okay, it's very simple. And then we can approximate according to the Levy property to all of the Levy measure, satisfy the usual conditions. For this part, you know that if we consider the N, the Gaussian space-time white noise, that there's no potential parts. You know that for all the whole space, there's no invariant measure. If there's no potential, of course you have the potential, it can be true. But if there's no potential, it will no invariant measure. For the bounded interval, it will always have the invariant measure. Now our case is a half-line. So you can know whether the half-line you want to know perhaps for the half-line, does the invariant measure exist? Okay. For our proof is very simple. Perhaps it will be no. We only explained here simple. Plain it. Okay. Here we just add this part, or the potential part. Then we can let the epsilon go to 0. We know that for this under this invariant measure, okay, I know that the mu epsilon is the invariant measure for this system. So okay, so under this invariant measure, we know the path is nothing but the OU process. Here we consider the x. In some sense, it has the effective as the time, because our x is half line. Okay. Now we let epsilon go to 0. Here is go to 0. When go to 0, it's nothing but the Levy process. So in this case, in very simple idea, so we can show that the Gauss process, the Gauss measure, Wiener measure is the invariant. Of course, in this case, it is the classical invariant measure. Classical. I mean that because there is no jump part, it's just a macro process. Okay. Now, our main goal is want to characterize the invariant measure. So, as the converse problem, it will be equal. Okay, at the beginning we think it will be equal, but to show it we meet some difficulty, we use some additional or technique condition. Okay, we want to consider the measure supported by this space. So this means that the ux will be at least increased in the linear growth with the linear growth. Okay, and we assume this one. It means the expectation of the Levy process will exist. So why because it's just according to this part. Because if we want to let the path of the Levy process satisfy this condition, it must satisfy this one. Because our Levy process is one-dimensional. According to the large number, it must satisfy this condition. Okay. So in this case, we know that. Okay, I write down the L. Under the second assumption, we know that the convex hull is a subset of L. Okay. So under the additional condition, we can show that it will be equal. But under the additional support condition, I must require the support in a good space. Okay. The proof is very easy because for the meaning of invariant is very weak. So and the solution and the system is only a linear and in some sense Olympic OU process. So we can choose an initial value U0 such that it's distributed as the measure mu. Then we can minus two equations with different solution U0, and x is the solution of the path of the Levy process. Then we will show that for t the limit, in fact, this is our goal. Okay, we want to show that the UTX must be in this space, Then, after I show this one, then we can know that the UT, this is a lemma we have to show. For each fixed t and t, for each fixed x, when t go to infinity, it is just this way, linear. Although this is the convolution of the with respect to the heat kernel. Okay. And then this one, because we assume the large x is the path of the Levy process, then we can show that this part hold. Let t go to infinity. So this is the law of Levy process. This is the law of Levy process, and this is the initial measure. So this means that it's nothing but must in the convex Hall. Okay, now I want to give some remark, or we want to compare the result with this kind of OU process. I want to give some. So here the B, you know that, okay, sorry. The B will place the rule of the TILs of function in the deterministic model or interface model. And because the heat kernel satisfies this condition, we know that for our half-line case, the invariant measure is not unique, depending on initially comes this property. It's not unique. Okay, but we can show that the law as a measure in this space, we can show that it's infinitely divisible. Okay, now this is another remark. If we consider this equation, here LS denotes the Levy process in some proper Hilbert space. We know that if the ST is an exponential stable, if that is some exponential stable, and the Levy measure satisfies this condition, this is sufficient, necessary and sufficient condition for the existence and uniqueness of invariant measure. This is just like the finite dimensional case. Okay, they also called the operator self-decomposable variable. You know that for the finite dimensional case, the invariant measure of this equation, here is the infinite dimensional divisible measure. We know that as a subset self-decomposable measure, this is the invariant measure. From this is the invariant 1 to 1. Okay, this is well known. It's just a subset of this case, subset of infinitely divisible case measure. Okay. From the result, we can't see any more information about the support of the invariant measure for the infinite dimensional case. In fact, we can show that if we consider a heat equation, we can show that it will be continuous in its spatial variable. This is result I just take from the paper of Reznik and Zelzik published in this year. Okay. So from this theorem, here the delta 0 must larger than one half. Then for any delta less than delta 0 minus one half. Okay, sorry, there's a mistake. So from this theorem, if we consider the heat equation, it means gamma equal to 1. Then for any alpha, here alpha, the LT is the subordinated process. The W is the L2 cylindrical Brownian motion, and zeta T is 1 alpha over 2 alpha stable subordinate process. Okay, so for any alpha, it will be continuous in its spatial variable. Okay, so from this theorem, we know that if you want to see that the law of Levy process is invariant measure, its fields. No, it's not possible because the path is continuous. The support, not Cadillac, must continuous. Okay. Therefore, our purpose and our result is very, very different from the usual Levy noise. This also tells us we can't try to construct a system with the law of Levy process as its invariant measure by the Levy type noise. It's not possible, because they has good spatial regularity. Okay. Now I have 5 minutes, so I want to. You know that if we consider a potential case. Okay, for good potential, so we know that there exists the Gibbs measure or something. It's well known. So our trivial question, just as our linear case, we can construct such this measure will be, in some sense, will be invariant for some system. Formally, we can repeat our idea as we explained it, but we meet some critical problem. So why it's very trivial to know that we must consider such SPDE. For the potential part, it will become very complex. And we can't know how to control this part, how to define the integral for this part. Of course, okay. So when I explained our idea to somebody, they asked me for our case whether we can consider the fractional Laplacian for this case. Whether we can construct the invariant measure will be the law of Levy process. From this theorem, we also can tell we can't because the path is continuous. Okay, that's all. There's some reference. This is just the last theorem taken from this paper. Okay, that's all. Thank you. It's
Yep.
What is your motivation for using your type of noise in SPDEs and heat equation?
the motivation.
Yeah, apart from the fact that you show that the support is not for the invariant measure in your sense is not in C but in square word space. There's something more?
Okay, sorry. So the motivation, in fact, it's very, very simple. In fact, if I just now I see that if we consider this equation, the Wiener measure is invariant. So as Wiener measure is nothing but the law of Brownian motion, we also know that as the general usually we consider, to generalize the Brownian motion, we'll consider the Levy process. So, our question is just from the law of Brownian motion to the law of Levy process. Whether we can construct, because at that time we know that in the somebody will from this year there's some papers to consider this equation, and they can characterize the invariant measure. Perhaps you can know, you can think that the invariant measure is nothing, just as the Gaussian case. Perhaps it can be the law of some Levy process. In our case, we want to know that whether it's impossible. In fact, it's false. It's false to consider such this equation to consider its invariant measure will be a law of Levy process. Our goal is very simple.
I mean, are you doing something a little bit unusual in the sense that, you know, the Levy noise would produces some discontinuities, but these are immediately erased by the smoothing of the heat kernel. So it, you know, at least on an intuitive level, you would not expect to have a discontinuous process in X at a fixed time t.
Yeah.
But maybe sort of mixing, so you obviously need a noise that sort of remembers the discontinuities it's seen earlier in some sense.
Mm-hmm.
But wouldn't it be more natural to try to have the Levy processes as invariant measures of other sorts of SPDEs where discontinuities are not immediately erased? I'm thinking of, say, the wave equation, which is sort of a natural choice. Or even the damped wave equation, which would include a first order and time derivative.
Mm-hmm. Sorry, I don't know.
Another short question. If you take a finite dimensional system
Mm-hmm.
and you say, I want to find under what conditions I get the marginal of the Levy process, an infinite divisible distribution as its stationary measure.
Self-decomposable. Yeah. It's just
Self-decomposable, but self-decomposable, okay, you know, but something different. You know what? How do you do it? Because the problem is that these Levy measures are not very well tied with linearity. If I have a linear function, if I have something like du over dt equals au plus noise,
Mm-hmm.
I cannot go beyond that unless you put some noise in the A as well. It's hard to get. It's hard to go beyond this thing, even with a finite dimensional system. Anyway.
A comment to Robert's comment is
Thank you.
is that I know examples of Gaussian measures which are invariant for deterministic equations, and it's therefore possible that similar equations can be PDEs, I mean, can be constructed for Levy measures. I don't know, but certainly I can provide a reference to an PDE of first order which has a Gaussian measure as an invariant measure, a truly linear measure.
You mean deterministic?
Deterministic equation, yes.
So it's linked to the invariance of the PDE. So if the PDE has a conserved quantity and the quantity is of energy, then e to the minus the energy is the invariant.
In this case, it's not. In the case I have in mind, it's not.
But that's an answer to the question of construct.
How does that relate to my comment?
You are saying that you can have different SPDEs which have the measure invariant. I said that instead of even SPDE, you can have PDEs.
Okay, so let's thank the speaker again.
Thank you very much.